to introduce the first speaker of the first afternoon session after lunch. It's Eisert from the Free University of Berlin, where everything is free, and he'll be talking about boson sampling and the reliable quantum certification of multi-photon interferometry. And I will stand up and glare at you about the 5 minutes at the end. Okay?
Very good. So thanks so very much for the kind introduction, and thanks to the organizers for the effort and sweat of setting up this wonderful workshop indeed. So this talk will be about something pretty much everybody else was also speaking about, namely boson sampling and the reliable quantum certification of multi-photon interferometry. That's the beauty and charm of a strong and focused meeting like that things overlap and come together. So this will be about variations of the theme, in fact 2 variations and a coda at the end, very much related to what Matt and Andrew and Ish and loads of others presented very nicely in their talks yesterday and today. However, with a slightly different mindset and twist to the story. I should also apologize for being late at the meeting, so this is my excuse here. I had a bit of a tricky week, and yeah, what can I say? I should also admit that this is a bit of a superset of a talk I gave earlier this year at PQE, although with more kind of ramifications and meditations at the end, depending on how it goes with time.
With that talk, I can fall asleep now.
Totally.
No.
You're the chair.
I'll take my watch.
Give me a hard time in the very end. Okay, so enough of the disclaimers. The chairman is already falling asleep. So, okay, to remind you, this conference is on multi-photon interferometric devices, and this for very strong reasons, for these beautiful applications in metrology and imaging that we love and appreciate, and also for linear-optical devices thought to have superior computational power compared to classical computers and devices. And that's not only true in the sense of the fully fledged universal Cale-Eim-style quantum computing, but maybe more feasibly so experimentally in the sense of just taking photons, sending them through multiports, and the pattern of correlations emerge to be so intricate that it can presumably not classically be efficiently simulated. So as we have seen many times already, and will hear many times later this, well, I guess tomorrow, boson sampling, as it's called, can presumably not be done on classical machines. So far so good. So the question in the focus of this talk will be, right, we go into the lab, we have done this, and we ask, is the thing that we've been doing actually the right thing? Have we achieved the goal? So how would we know whether the device that we have in the lab is actually properly functioning? And here we again at the theme of Ish, Matt, John, Andrew, and lots of other people at this meeting. So this is the topic we will have a look at in 2 variations and a coda. So the first variation is the variation on boson sampling that we just briefly revisit. Never underestimate the charm of seeing what you already know. So as we know, the point of boson sampling is that that's the setting. You would think of sending n photons in m modes through a linear optical multiport that linearly transforms one set of bosonic operators to a new set of bosonic operators. And at the end of the day, you just measure the output pattern of photons. So that's the set of integer output patterns, and you would just sample from that distribution. So let's do the experiment. There's 4 photons coming in here. So we do it, and what we get is 0, 1, 0, 0, 0, 0, 1. So it again, 1, 1, 0, 0. It's random, that's the very point. It's kind of a quantum Galton board. Now as we know, the probability of getting a certain outcome in this pattern is given not by the determinant but by the permanent of a submatrix of the unitary of the matrix that governs the unitary multipole. That's a UM element governed by the pattern of photons detected. And as we know, to compute the permanent is a sharply hard problem, but actually, that's not quite the problem that we have. In order to be able to efficiently sample from that distribution, one does not need to be able to efficiently compute the probability. That's a common misunderstanding. And moreover, what's true that if you know to compute the probability distribution, it's not quite clear how to sample from the distribution. But nevertheless, it's been the insight of Scott to see that still this problem is in a way, a computationally hard problem to sample from that distribution. So that's kind of the layman's version of stating that expression, that to sample from a distribution that's not perfectly right, but only close in the total variation distance and the one norm to the Boson sampling distribution is in a way computationally hard, with high probability if the unitary U that's describing the network is chosen from the Hahn measure, and M, that's the number of modes, is increasing sufficiently large with N, the number of photons. So that's true in the sense that if that was possible, then one would have a collapse of the polynomial hierarchy, which is thought to be highly implausible. So for that matter, it's a computationally hard problem. So people were thinking, wait a minute, that's great news. So in order to have a device that's presumably outperforming classical computers, one does not need to have this kind of fully fledged, full Monty, KLM style universal quantum computer, but instead one can go into the lab and send photons to the multipole to detect the pattern at the end of the day. And what is more, there was this very exciting development on waveguides on top of atom chips, on integrated optics, to have like modes on waveguides and having beam splitters realized in terms of evanescent wave of modes overlapping in the lab. So there was a flood of beautiful experiments by all the leaders of the field that realized such boson sampling devices in the lab in very beautiful experiments indeed. Okay, so far so good. So for the purposes of this talk of certifying things, so okay, let's assume we have done that. So let's go into the lab, but actually, well, how would we know whether we are correct in the first place? So you experiment sample that they deliver long lists of numbers. So how would we know that the list of numbers obtained is actually the right list of numbers? How would we find out? Well, there's several kind of readings and ramifications of this, which make perfect sense. So the first ramification or reading of this setting would be the one where one just kind of goes into the lab and looks at lists of numbers and just argues from the list of numbers as such, to look at this as a kind of black box sampling problem. So that's, I mean, more technically put, that's assessing the problem from the mindset of a so-called symmetric algorithm, meaning the algorithm run would depend not on the labels used, and you can permute the list of outcomes in the setting. So in other words, you go into the lab and you just look at the list of numbers and argue, how can I discriminate that distribution from one that I could also otherwise get? That's the setting of black box sampling complexities, and assessing the problem of sampling from a distribution like that from the samples alone.
I don't understand what you're certifying. You're not certifying the unitary, no.
No, we come to that later.
You're certifying that the resultant distribution is within some epsilon by one norm of a Haar random generated boson sampling. Is that what you're certifying?
Oh, no. I'm just saying, no. We come to that later. I'm just saying I go to the lab, I get a list of numbers, and I'm looking now at the black box problem of discriminating that distribution, judged from samples alone, from one that I could have also otherwise obtained. I will mention that in a second, what that distribution would be. I'm not taking the unitary into account at that setting, because that's a plausible setting in this sense, because it's not quite clear how to make use of the information about the unitary as such.
I'm just trying to picture what your certificate will say. So you don't have a certificate, do you?
I come to that in a second.
Okay, got it. I'll say so.
Ask the question in a minute from now.
Okay.
Okay, so, to cut a long story short, so this is the black box setting as kind of certified black box as decision problems. I would like to reach a decision on the distribution just from the classical distribution as such, from a number of samplers of a given order in the natural system size of the sampling problem. So what we are doing here is So we set up like fingerprint matrices of two samples of a certain length, and here, well, there's a kind of developed machinery of black box sampling complexities where like CAB of the fingerprint matrix would be the number of elements that appear exactly A times in the first sample and B times in the second sample. So the technical exercise to be done here would be the one that one would develop large deviation bounds and estimates of random matrix theory that's quite similar to this formalism that's also used in Scott's argument of the type, like if you have a unitary, that submatrices would very much look like Gaussian ID randomly drawn matrices. So to come back to Barrett's question, so at the end of the day, if you put that together, the argument that you arrive at, that should answer your question, is you get a list of numbers, and you would have that for n, like arbitrary, and m chosen appropriately as the number of modes, and for H random unitary, it is with probability that's supra-exponentially close to 1 in n impossible to decide from polynomially many samples whether with a symmetric algorithm whether a given black box samples from the Boson sampling distribution or the uniform distribution. Yeah, so in other words, you go into the lab, you get a distribution, you get a list of numbers, and just looking at the samples alone, you will not be able to discriminate that distribution from just the uniform distribution spitting out uniform random patterns from these polynomially many samples. Yeah, which of course can be classically efficiently simulated in the first place. So, is that distribution uniform? No. If you just set up the decision problem of the type, can I discriminate the distribution from the uniform distribution? That you can, if you have no other information about the distribution as such. But if you just look at, with symmetric algorithm, at the list of numbers, it will just look perfectly uniform. So it gives a kind of rise to an interesting situation, an intricate situation that, yes, to do Boson sampling is, in this sense, mentioned a hard problem, but at the same time, if you look at the list of numbers generated, they cannot be efficiently discriminated from one that you also could have efficiently generated on a classical computer, namely the uniform distribution. Yeah?
So I hate to interrupt, but I'll
yeah,
just...
sure.
No, you
If I don't
don't.
get this, I won't get the rest. I mean, first of all, you say impossible to decide. It's always possible to decide, you just can get the wrong answer. So, no, seriously. Like,
Okay.
But then when you go further and you say, okay, you make a decision, and the result of the decision is yes it is or no it isn't,
Yes.
then you can, it might be possible to get a yes when it's yes most of the time or no. You know what I'm talking about.
Okay.
Can you tighten the statement a bit? Or do you want to stick with saying it really is impossible to decide, even wrongly?
Well, it's not, well, I mean, it's not more possible to decide than you would just, it's in the sense of a decision problem, right? I mean, maybe that's something to be sorted out later. You would not be able to more likely say, give a correct answer than the wrong answer. It just looks, for all practical purposes, you set up a black box problem, the kind of a flag goes on, and the probability of you being right is just as uniform.
Okay,
You're not
you're
gaining any information of that type with that type of algorithm.
Okay, so you're saying it's impossible to get an answer that would be better than a random.
Exactly, that's what a kind of decision in this context would mean. That's exactly that. Of course, by accident you can be right, but that would be just like flipping a coin. Yeah? So, this is like for a symmetric algorithm that looks at the samples as such, but of course you can also look at more general algorithms that take all the information available into account. This is kind of the technical way of phrasing it. So you draw U as H random, then with probability as least 1 minus delta, and for every t and every epsilon, there exists a circuit of a size that's slightly larger that samples from a distribution that's epsilon indistinguishable from the collision-free part of the Boson sample distribution by circuits of size at most t. What does that say? It says the following, that you have a circuit in the lab. So for every quantum circuit, there's a slightly longer classical circuit that cannot be efficiently distinguished from the quantum output. So in other words, you have the machine in the lab. So there's evidence that Boson sampling is hard. It's a perfectly valid statement. At the same time, it's true that the Boson sampling cannot be efficiently distinguished from one that is perfectly classically efficient in the first place. So it's a bit like this situation that you claim to have a boson sampler in the lab, which is kind of outperforming classical computers. At the same time, you could say, cheat on me and say, you just take your iPhone, put it into a box, and program the iPhone that it spits out random numbers, and I would not be able to falsify you that you have not a quantum device, but in fact just an iPhone in your box. Yeah, so it's a bit like saying, so yes, boson samplers are more powerful than classical computers. I mean, presumably under these mathematical assumptions that enter, but let's take that for granted. So it's a bit like saying, I have a, it's like, I like to say that, like if I'm claiming I have a supercar, or you claim you have a supercar, like a car that's more powerful than any car available. I look at the car, and I look at it, it looks like a Fiat Punto, say. Okay, fine, I mean, no offense, Fiat is a great car, but it's like a car. I enter it, I think it's a supercar, so I would accelerate. Well, it accelerates like a Fiat Punto, right? Then I say, okay, fine, let's go to the motorway, left lane. Well, I mean, it accelerates like a Fiat Punto on the left lane, I brake it. It must be a super brake. Well, it brakes like a Fiat Punto. So in every operational way, it would feel like a Fiat Punto. Yet it's a supercar. But in this sense, like it's a powerful car, but it cannot be discriminated from one operationally that would not have that ability. Yeah? So that's a kind of interesting twist in the situation. Yes, boson samplers are kind of analog quantum devices that outperform classical computers. At the same time, one can argue that to the extent that it can be classically efficiently verified, it would not be more powerful than a classical machine. So that's kind of an ironic situation that's not a contradiction, it's perfectly valid. Yes, boson samplers are more powerful, yet they cannot be discriminated from one that would not be powerful, like in the sense of the symmetric algorithm, just to spit out random numbers IID from a uniform distribution that I can program my iPhone within like 3 lines of code. Yeah?
Yes. So when I first read that, and even maybe now, it wasn't immediately clear to me how that was different from just the overall point anyway. Right? I mean, the point is that, you know, if I put 30 photons in 900 modes, then it is hard to calculate that classically. So, you know, of course an experimentalist could just always give you any, I said, you know, here's the output, and, you know, I know that you cannot verify, that's the whole point, right? So it wasn't immediately clear to me how your message is different from that.
Well, the thing is, I mean, the question is not whether you can compute, again, I made that point earlier, like whether you can compute probabilities or something. But I mean, you cannot, but that's not quite the point. It's a common misunderstanding that you think you have to compute, you don't have to. To approximate the distribution, you would not be able to do that. But the thing is, for purposes of efficient classical verification, you would not be able to discriminate that from anything that you could also classically efficiently simulate. So with just, in other words, there's always a kind of classically efficient explanation of the same finding that would be perfectly classically efficiently realizable. That's kind of the point. Yeah? So in this sense, I mean, that's not a contradiction, that's perfectly compatible, but there could have been a classical story that gives rise to the same outcome. That's kind of the point. Yeah? Yeah.
And is that different for a full-scale quantum computer?
Of course. I mean, well, I mean, for a kind of universal quantum computer, if you can run NP problems, you have like a witness, you can check NP whether Shor's algorithm, you run it, and then you would kind of check whether the outcome is correct. Of course, that's different. In fact, so this is the kind of the first message. So in this sense, this device looks, it's like a powerful device, but it looks as if it had been generated by a perfectly classical efficient device. So it's like a, in this sense, it's indiscriminatable in efficient ways from a classically efficiently programmable device.
But yes,
this is maybe too much to ask for, yeah?
This sounds like a problem with sampling, not much less boson sampling. In other words, if I gave you 2 classical sampling machines,
yeah,
I would also have the same problem, right?
Oh, no. I mean, no, that's not true. I mean, of course, that's kind of what I said. Of course, it's, I mean, in many settings, perfectly possible to discriminate distributions. So it's just like, like the technical argument, I mean, this is like a flat distributions, like the intuition rather is that every outcome is very unlikely. They're epsilon flat or very small epsilon. That's the thing. And in this sense, it's kind of not discriminatable with a symmetric algorithm from the uniform distribution. But of course, you can discriminate lots of samplings from lots of distributions perfectly well. So
this is special.
Totally, yeah. This is kind of originating from the flattest distribution in a very specific sense.
Okay.
Yeah. Oh, 20 minutes. Okay, I have lots of slides at the end, but I can also cut kind of the meditation a little bit. Never mind. So, okay, fine. So, the boson sampler is in this sense not discriminatable from a classically efficiently simulatable device, but maybe that's too much to ask for. So, if you go into the lab and you would get evidence that your device is actually functioning on the level of quantum state preparation, then you might take it for granted that the actual sampling done at the end of the day would also be right. That would be a kind of a pragmatic approach to the problem. So you could say, can I efficiently certify quantum circuits as such with local measurements, letting aside all the sampling, but can I just look at the state preparation as such in quantum efficient ways? That relates to your talk and to Ish's talk and so on in a slightly different setting. We don't look for unitary states or circuit measurement or something, but we ask for state preparation in a very strict sense, namely, of the type of a linear-optical preparation, where you would have single photons coming in and a passive circuit following. You would have a continuous variable setting where you have like vacuum coming in and a Gaussian passive or active circuit or squeeze state coming in, two more squeeze states coming in one way or the other. That would be the familiar continuous variable setting that Akira was speaking about. Or you could think of post-selected instances like of the KLM type would have like certain photon patterns coming in. You would post-select onto certain outcomes of the photon patterns and then you would condition on that type of outcome. So that includes most, in fact, all multi-photon state preparations. Well, not quite all. I mean, maybe the hybrids not, but most multi-photon state preparations that I'm quite aware of. So what we are asking for is, can I go into the lab and certify now the state preparation on that level to all beauty and glory accuracy as a one norm outcome estimate of knowing that you are within a certain approximation of the true state. So what's the healthy mindset of looking at that? This is like similar to a kind of interactive proof system in computer science, where you have a single round of interaction, where you have two players coming into play. The skeptic certifier Arthur which is almost classical. It has a kind of a classical computer sitting there, and with very limited quantum capabilities, namely single mode homodyne measurements, who wishes to ascertain whether an all-powerful or like an untrusted quantum prover that presumably has more quantum power, namely has access to the full preparation of the quantum circuit, under imperfections, of course, and also under cheating. So Merlin can also cheat, can indeed prepare a quantum state up to a certain target fidelity. So the setting is this almost classical guy Arthur would like to go into the lab and find out, using only the single mode measurements, whether the state in the lab is actually the one that he has kind of asked Merlin to prepare. So what is a natural setting of that kind? So in principle, what you would want or would dream to have is you go there, would like to know, am I close in fidelity to the anticipated state or not? Fine, but this is of course naive. That's not going to happen because of imperfections and inaccuracies. Of course, you cannot just say I'm closer in fidelity to the target state or not, because at the boundary you will always make a wrong judgment. So the healthy approach is to say that's like in the sense of a weak membership problem, that you would have a delta, like a buffer region around it, and you would either say that you are kind of closer in fidelity to the anticipated target state, then you would accept the state, or you are off up to a delta, and then you would reject the state. That's kind of a healthy setting. You go there, and whenever Arthur would accept the state, then he would necessarily be inside that fidelity ball around the anticipated state, which would give rise to a one-norm estimate of the state in the lab. That's the robust certification setting. What can be more practical is the one on the right-hand side, where you say, I reject all states outside the fidelity ball, and I'm only promised, it's called soundness, and what's called completeness is that you only are promised to accept the true state, but of course you can accept also more states, but any state you would accept would necessarily have a fidelity better than the ball around the anticipated state. So, and then look at the fidelity lower bound that emerges from the counter-propagated anticipated state going backwards under this circuit in this sense above. So the advice would be, so Arthur goes into the lab, he chooses what he wants to have, the target's fidelity, and a maximum failure probability, an estimation error epsilon. From that he would classically efficiently compute the number of copies C, which provides a classical description and gives that description to Merlin, who would then prepare C copies of that anticipated state, or at least claims to have prepared the anticipated state. Then Arthur would make the measurements, like homodyne measurements, and if he estimates the fidelity in the right way and would accept that, he can be sure that the state in the lab is exactly up to this fidelity ball, the anticipated state in the lab. So how can one measure this this fidelity? So this I cut a little bit short. That is based on a kind of a non-Gaussian nullifier setting, but practically the point is that it requires only single-mode homodyning and two-point correlations in homodyning as the practical measurement. In any of these settings, you can unambiguously certify that you indeed have the anticipated state in the sense that I just said. So what is true is that both in the linear-optical setting, so single photons coming in a passive circuit, then with a number of measurements that is efficient in everything except the photon number, so specifically in the number of modes, you can perfectly efficiently certify that the state is close to the anticipated state with all beauty and glory and as a one-norm estimate, that once you accept you are close to the state, and the same is true for the Gaussian setting. So with poly effort you can certify whether your state is the right thing in the lab. So that's of course much more efficient than tomography, which would be inefficient in the number of modes. So if you just want to know, I know what I think I would be having, can I test, can I check whether I have done the right thing in the lab, this is perfectly efficiently possible. Yeah? So this is a slightly different setting. I just want to anticipate what I would want to have, and I can check, do I have what I think I have? That's less than tomography. But if I just want to know, I think I should be having something, I can check whether I'm right, and I'm not, this is not like checking unitaries or something. I'm not assuming that the state is close to something. There's no assumption whatsoever, but efficiently you can check whether the state preparation has been right in one way or the other. That also works for post-selection. Well, that's more technical, but in the same way, efficiently you can also assert that the state has been right. It's also true in the robust setting, where again you have a boundary, in the sense of a weak membership problem. You can, at this buffer region, the test says whatever, but if you say you have it, you have it. You go into the lab, Arthur makes these measurements. They are polynomially many in the number of modes, and you would know that your state, if accepted, would be inside the ball of the anticipated region. So, lesson: if one just would like to know learn about the state preparation as such, not the kind of the sampling at the end of the day, but if you just want to know, has the quantum device as such be right and the state preparation be right, then this can be done, and this can be done even efficiently in the number of modes. not in the number of photons, but in the number of modes. You can do that, and that's much more efficient than tomography, which would be exponential in the system size, with feasible local measurements. So you just do homodyning. The physics is very simple. You do like a single mode and two body correlated homodyning measurements, but from that you would be knowing that if accepted, you have the state in the lab unambiguously. Okay, so this is kind of the ultimate step. You can really kind of certify, like once you accept, it would be in the strongest possible sense. There's no gimmick, no joke, no approximation. I mean, only in the sense that you know that in the one, so the tightest possible sense, you would have the state in the lab. So in this sense, efficient state verification is possible. That's less than tomography, but it's also not about the sampling problem, but if you just want to know the state preparation has been right, this is perfectly efficiently possible for a fixed number of photons. Okay, so 31 minutes into the talk, so I have some time for like some final musings, say, where I make a kind of selection of final musings. So, okay, first we look at the sampling problem. Second, we look at the question of certifying the state preparation, which is less than tomography, which would ask about the learning of an unknown quantum state. But sometimes, of course, you would want to do tomography in the sense of you have an unknown state and you would want to have like actionable advice of knowing what experimental parameters to tweak to make sure that, like what to change in order to make the experiment right. And we've been working over the last years quite a bit on kind of tools of tomography for quantum many-body systems, for like many modes of the type we just said, but also called atoms, trapped ions, and so on in different ramifications, taking the signal processing aspect of things seriously. Maybe only give one example of that type, which is related to the Netflix problem, as follows. Okay, so you might know Netflix. It's a kind of video online rental place.
No Netflix in China.
I noticed that. Actually, in Germany, it was just introduced last year, to my astonishment. But I presume that it's been immensely successful in the rest of the world outside China and outside Germany, with an immense number of customers where you can download or stream videos. That's kind of the copyright issue, right? You don't download, stream. Never mind. There's lots of videos, I think all available, are kind of there. And, well, you can stream them, watch them. And obviously, Netflix, being a major player, has an enormous economic incentive to find out what movies people like. Right? I mean, because if they know what they like, what people like, they can adjust the advertisement in the right way. So people can rate videos, I mean, with, I think more than up and down, there's a kind of entire scale, but there's a number of movies which is very large, and the number of users which is essentially infinite. A good approximation to infinity, which is a huge matrix of what movies people like, which is a great thing to know. Except Netflix doesn't know it, obviously. This is rather how the matrix looks like. It's like only a couple of dots because people may have a lot of time, but they can only watch a number of movies. They will only rate a tiny fraction of the big number of movies. So Netflix would like to know how the rest of the matrix looks like. So they offered a 1 million award to the solution of the problem of how to fill in the rest of the points of that matrix. So how can I predict the missing entries? Was kind of $1 million problem. And you say, well, how would I? It's missing, so how can I know? Right? Well, not quite, because, well, tastes are not random. So people have preferences, and that means that, well, to a good approximation, the columns of that matrix will, in one way or the other, be linearly dependent, capturing the tastes, which would mean that the matrix given would have approximately low rank. So the mathematical question is whether one can reconstruct a low rank matrix from a comparably small number of matrix entries alone. And this is what's called the matrix completion problem, a variant of compressed sensing that was introduced by Kanders and yeah. So our big contribution, so to say, here some years ago was to find a general theorem on matrix completion, arguing that a matrix, a rank R matrix can be recovered, not with all points, like not n squared points, but only Rn polylog n randomly chosen measurements of the type trace AI rho, with AI being unitary operator basis. The reconstruction is probabilistic, but it will only fail with an exponentially small probability. The efficient is exact, it's efficient, and it's robust in the sense if I tweak a little bit, my reconstruction will also be tweaked only a little bit. There's no gimmick. I mean, it's as practical as it sounds. With very few data points, comparably, you can construct a low-rank matrix.
Did you get $1 million?
That's interesting because
No.
no,
You wouldn't be here, I think. if
no,
you-
and in fact, the irony is that even this paper I just mentioned was just published like 2 weeks or something after the award was given. So it's interesting that the first solution was rather practical, but a much better solution, namely the matrix completion solution, was published 2 weeks later, which was not the one that was awarded the prize. Yeah, it's a bit of an ironic twist, but that's of course now the way you would do it. That's the most efficient way of doing it. Anyway, so of course you will already see that since Pauli matrices do the job, this is nothing but the low rank tomography problem. Like if you have a matrix that's approximately low rank, like approximately pure, approximately not full rank, then this is the way how you can think of tomography of an unknown state. And so this we proposed some years ago. In the meantime, we've been taking the statistical aspect of things seriously. We joined forces with the Cambridge Statistics Department of thinking of error bars. That's related to your issue on bootstrapping and then making regional estimators. So this is what we've been doing on this since then. Also, we've also applied this with the blood gang on the tomography of topological color codes for the 7 trapped ions. So the lesson is, if you want to do tomography, like really learning about an unknown quantum state, but which is approximately low rank, this can be done much more economically, much more with significantly less effort than kind of naive for tomography. So this game goes further on. So here, this I will cut maybe a bit short in the sense that if you're in the true many-body setting, like many-body states or even quantum field states, of course, tomography must necessarily mean that you are within a statistical model and you just say, can I say within matrix product states or continuous matrix product states, find the state that is compatible with the data. By taking that seriously, one can do like tomography of even of quantum fields, where you can bootstrap from low-order correlation functions, high-order correlation functions, like in cold atoms on top of atom chips that we recently did with Jörg Schmiedmein's group in Vienna, where one does quantum field tomography of such continuous quantum systems. But let's maybe come back to so there's kind of, one can think of efficient tomography of such many-body systems or quantum many-body systems. But let's maybe come back to the original setting of boson sampling and kind of these analog simulators in one way or the other. So boson sampling is a purely kind of conceptual device. It doesn't, well, you heard an application earlier today, but that's just within the physics scope, so to say. So the sampling as such has only the application to do something interesting. I mean, it's only a kind of a mindset device that's only set up to do something hard. It's a kind of a prototypical setting to see in what way one can have something in the lab at present technology that does something more powerful than a classical computer, no matter what. And that relates to this notion of quantum, it's a stupid name, I mean not stupid, but a bit of a evil name. This idea of quantum supremacy that John Preskill coined not too long ago, jokingly, semi-jokingly in his blog, of just kind of going to the lab and with present technology just realize something in the lab that presumably outperforms classical computers as a conceptual device, no matter what. So boson sampling is indeed a good candidate of that type of setting that, under the assumptions made, it outperforms classical computers, but at the same time you have the ironic situation that it's a device that outperforms classical computers, but you go into the lab, and it's a bit like the Fiat Punto, that for practical purposes the output distribution generated looks as if the device that you had there would also would look like a classical device, in the sense that it would not be efficiently discriminated from one that would perfectly spit out the numbers that you give from a classical machine. So you could put a black box, you have an iPhone in it, it would spit out numbers, and there's no way to discriminate it from the true Boson sampler, although it is a more powerful device in this sense. So this is a bit of a kind of ironic situation of the output distribution not efficiently being discriminatable from a classical, efficiently comparable distribution in the first place. So one could kind of let the mind wander a little bit. I mean, you asked that in a way. So it's that kind of intrinsic to the game. So if you have or you asked that, if you have a kind of Shor quantum computer, of course you can check. It's an NP problem, and if you have an instance, you have a witness to check whether your numbers have been right, and you can just check the correctness of a solution. So in this sense, the verification problem doesn't appear in the same fashion. But here is rather the setting of an analog computer. You go to the lab, it's kind of hard, but the very hardness of the problem seems to make it impossible to efficiently classical certify, because say you go to the lab and the outcome is 5, but if it's a hard problem to find the 5, how would you know that you are correct in the first place? Do you see what I mean? So it seems a bit like the hardness of the problem with quotation marks and the impossibility of efficient classical certification seems to be like two sides of the same coin. So one might think whether whenever a quantum simulation is in a way hard, one cannot efficiently certify the correctness of the...
This is an example of the universe telling us again that there's no such thing as a free lunch.
It's kind of like that. And this is a bit of a pity, because, I mean, there's this whole field of quantum simulation, right, where you want to have a device in the lab that presumably outperforms almost done classical computers, and you go into the lab, you get data, but at the end of the day you will never know whether you have done the right thing, because it's an analog simulator, you get a number, is this correct? How would you know? It's a hard problem. Yeah? But the last point I would like to make is, well, not quite. There are settings where there's free lunch, that it's a slightly different setting that this gentleman in the back and Emmanuel Bloch and myself looked at some time ago, although at that time we were not quite aware of that aspect of the story. But in these quenched cold atoms, like many body settings with a local Hamiltonian, you have the situation that you do something, you can efficiently, classically verify that you have done the right thing, but you cannot predict what comes out. So in this sense, there is free lunch settings where you can create many-body systems, you get some things happening. It's an analog simulator, in a way simulating itself. At the same time, you can know whether you've done the right thing. You can keep track of things, and when the flag goes on, you have done the right thing, but you cannot predict what comes out, which is the quantum simulation at the end of the day. So there are, in this sense, free lunches that you can efficiently simulate devices that, in this sense, cannot be efficiently kept track of, so are true analog quantum simulators in this. Okay, summary, we looked at boson sampling in several ramifications. We looked at the problem of classical certification and found that even though a boson sampler may solve an interesting problem, it cannot be efficiently classically discriminated from a device that would be like the iPhone, that just spits out numbers. That's not a kind of, it's not a bug, it's rather a feature. It's perfectly compatible. You can have that, while at the same time you cannot discriminate the outcome from a classically efficiently preparable device. We look at the question of, wait a minute, if I just want to know whether my machine, my quantum machine is right, as a state preparator, you can perfectly do this classically efficiently in many settings linking to your talks, but here not in the sense of a unitary estimation, but as a full state preparation setting in the sense of a full one-norm estimate. And there's even like free lunch situations where you get this kind of, well, quantum supremacy in a way where you outperform classical devices. You know that you've done the right thing, but you don't know what comes out at the end of the day. So, thanks for your attention. This is the summary. So over here we call random number generator. 9999, are you sure that's random? Well, that's the problem with randomness. You can never be sure.
So we have time for a finite number of infinitely short questions.
Yep.
I'm trying to figure out how this work relates with the follow-up paper on boson sampling that was published last year on boson sampling is far from uniform. So are you saying that we can now have an Arthur that is classical in the sense that it uses classical light to differentiate between the boson sampling distribution and the unitary and the uniform distribution, or is the claim something else? So I'm trying to figure out how your claim relates to their claim.
Oh, so this is not so much about classical light this classical light would be like other resources coming in. That's very different. So here the point, there's a kind of hierarchy or different coordinate systems of settings. The first thing is if you look at a symmetric algorithm, not making use of the unitary, but just the samplings, the output looks uniform. And this is a theorem, that's what it is. Okay? You say, fine, I can do less and more at the same time, meaning I can say, I don't care what the distribution is, how it looks like, whether it can be whatever. I just want to know the answer to the question, is it uniform or not, as a decision problem. I make use of all available information. I don't care what it is. It could be green, red, blue, whatever. Is it uniform?
Yes.
This is perfectly efficiently possible.
Yeah.
But at the same time, there's a mock-up distribution that would again be classical efficient, that would also give rise to the same the same distribution that you've identified as being non-uniform. And that game never stops. In the sense that there's always something, and there's always a bit extra layer that would be classically efficiently doable, that just perfectly looks like everything you do. So in this sense, it's a bit like a race. Yeah?
So you're saying that they went one step ahead in the race, but there are many...
Exactly, but there's another step, and so on. This never kind of stops. Yeah, exactly.
So I think in the interest of time, we'll thank Jens again.
Okay, thanks.